Welcome back, ladies and gentlemen. In this video we're looking at motion with constant acceleration, and that will be every situation we're going to consider when velocity is changing. We're going to consider acceleration to be constant. There could be situations where we're not concerned with those. But before we look at accelerating objects, I want to consider actual constant motion where acceleration is 0 for just a second. If we were to create a velocity time graph of an object moving with constant motion, well, then we would see a shape of the graph like this. It'd be horizontal line, the slope of that line would be 0, and right here, well, we knew it traveled for this much time, and right here we have our initial velocity, but we also have our final velocity is the same value. So the initial equals the final velocity. And when we look at the relationship like the equation for this line, well, recall this. It's the y equals mx plus b format for a velocity time graph for the line on a VT graph. But what we know is since the slope is 0, that's acceleration. There is no acceleration, and so that goes away. And we simply see that the final velocity equals the initial velocity. There's no change. Okay, so that's worth looking at and reminding you of. But we're going to look at this situation a little differently. Can this graph be used to figure out the displacement of the object? In other words, how far the object traveled. So this word displacement it's a word you want to know, and it simply means, well, the difference between your final position and your initial position. So displacement is usually delta D for us, and that's going to be our final position minus our initial position. Okay, so this guy is the displacement right there. Can we see the displacement? Can we learn about the displacement from this graph? And the answer is yes. Check this out. Okay, if we look at this line right here from 0 up to where the velocity is, well, that's just a velocity. And if we look at this line here from 0 to the end when it stopped moving or we stopped looking at it, that's a time. Okay, now is it possible to find the area underneath that line? And I'm going to use that phrase very specifically, the area under the line on the VT graph. So I'm looking at this area. Let me use a lighter color here. Looking at that area. Well, area is an easy thing, right? Let's see, a different color is going to stand out maybe here. So area. Well, what kind of shape is that? It's simply a rectangle. So area will be length times width. The length, I can consider, well, that to be the length maybe. So I have time. And then the width, if it's that wide, then the width is velocity. Well, what do I have if I multiply velocity times time? And because that's what's going on right here. It's usually written v times t. And, well, velocity is meters per second. Time is seconds. And so what do you end up with when you multiply? Look, the seconds cancel out, don't they? And you're left with meters. Whoa, 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 whoa. Check it out. Meters. That's a physical quantity that we are very familiar with. It turns out that actually is displacement measured in meters, right? So the area under a VT graph gives you displacement. I'll say that again. The area under the line under a VT graph is the displacement. If you can figure out that area, then you can know the displacement of that object. The area under the VT graph is the displacement of the object. That's fine. Quite easy. We know that, well, it traveled at a certain speed for a certain time. It's going to cover a certain distance from its initial to its final position. This, you've got to be very careful here. This actually doesn't tell us where it started, and it doesn't tell us where it ended. All this tells us, when we find the area, all this tells us is, well, how far away was the end point from the beginning point? We just know the difference between them. So that's all well and good. Now what, right? So what's going on next? What's coming next? Does this work? Does this idea work of finding the area underneath the line on a VT graph? Does that work when the motion is accelerated motion, when the slope is not zero? Let's take a look. So we have ourselves a VT graph. Okay, and I'm just going to do one of these things, like that. Okay, so we see that the slope is not zero. There is acceleration happening, right? And well, let's check this out. Can we figure some things out? First of all, we have kind of like a final time right there, yeah. So here is our length of time. And here, what is this value? That value right there is the final velocity. Well, where's the initial velocity? Initial velocity is right there where we started. In this case, it happens to be zero. Well, what about the difference between these? Isn't that difference your change in velocity? Sure is. So we're going to look at change in velocity, and we're going to look at time. And we want to calculate the area under this line on the VT graph. So I'm not looking at the whole rectangle anymore. The area under the line is just the triangle. What? What's the area of the triangle? Area equals 1/2 height times base. Usually written base times height, either way. We can do that because we know the base and we know the height of the triangle, and we just divide by 2 and we'll have our answer. So we're looking, remember, area equals displacement. So the displacement of this object is going to be 1/2 times the height, which is delta V, times the base, which is T. Ah, that's interesting. Look at that. And that would work, but this is kind of a special case. This is not an equation worth memorizing. And the reason why is right here. This is an equation that makes sense only when your initial velocity is 0. Right? So what if it's not 0? What if Pi is not 0? Right? Could we look at a situation like that? Well, sure. Let's check it out. We still have velocity compared to time, and okay, I need a non-zero initial velocity. I'm going to start up a little bit from 0. Give it one of those. So check this out. Now we still have your initial velocity. Do we have a final? Yes, we do. We have our final velocity there. Do we have a time? Yes, we do. From there to there is our time. And do we have a delta V? Sure we do. From initial to final, it's that difference. There's delta V. And our job is to find the area under that line. That looks like a weird shape though, right? So can we do that? Actually, yes we can. Absolutely we can. And the reason, the method we use is if we just look at this weird shape as a combination of two very simple shapes. Okay then. We're going to look at the area as being, well, you know, area is the displacement. But we need the area of two shapes. We have the area of a rectangle, which is height times base. And we're going to add the area of a triangle, which is 1/2 height times base. Okay, and that's going to give us the displacement of this object. Well, the rectangular portion, this guy right here. The height was this length right here. So that length is 0 to vi. Well, that tells me that that length itself is equal to vi. And multiply that by the base, which is t. You know what, I'm using height and base, aren't I? When I could have used length and width, same kind of thing, right? I'm just talking about that times that. Now, I will add the area of the triangle. I have a 1/2, that's going to stay there. And I have height times base. Well, the height of the triangle starts here and goes to there. That's a delta v. And the base of the triangle is t. Okay. Now this is looking nice and interesting. Triangle. I want to mark the triangle here. There we go. And the area of the triangle is that, and the area of the rectangle is that. Yeah. Okay. This is getting more interesting, but not so sure that's an equation yet worth memorizing. Again, it's not a bad one, and it's one you might encounter from time to time, but I don't know. I mean, the reason is this. Look, this is an accelerating object, and you don't know the rate of acceleration in this equation. It's not a part of this equation. And it would be nice if we had that in the equation. So check this out. I want you to recall the definition of acceleration. The definition of acceleration. Acceleration is defined as, that's what the sort of weird equal sign looks like, the triple lines. Is defined as the rate of change of velocity, the delta v divided by t. Okay, now this can be an equation. We turn that into a regular equal sign, and we rearrange it, and we say, you know what? From that, delta v is equal to, bring the t over here, acceleration times time, right? And that's going to come back in here. I'm going to substitute this into that. Here's what it looks like. We can say from our delta v equals, oh, this is page 3, sorry, I want to keep organized here. Delta v equals acceleration times time, and our previous equation for the displacement of the object, initial velocity times time plus 1/2 delta v times time. Okay, well, we're going to do this cool substitution, put those guys in there in place of the delta v. And this equation becomes the displacement equals initial velocity times time plus 1/2 acceleration times time times time. Okay. And of course that's going to simplify out a little bit. Boom. Now check this out. We have an equation that relates the displacement of the object to initial velocity and to time and to acceleration. This is an equation worth remembering. You're going to use it quite often, actually, in problem-solving situations. So off to the side here, I'm going to make a note of this. It relates the displacement, it relates time, it relates initial velocity, and it relates acceleration. So it's kind of talking about those things in the equation, right? What does that look like? That kind of looks like how you would list information when problem solving. Hint, hint. Now, another thing I want you to recall, I want you to remember that you have an equation for final velocity that relates acceleration and time and initial velocity. So there's that guy, right? I'm going to put a box around that guy because, again, you use it quite often. So this guy relates final velocity, initial velocity, acceleration, and time, right? Well, um, so we have these equations, but what if there's a situation and we don't know the time? Can we relate displacement and initial and final velocity and acceleration when we don't know the time? Both of these have time in it, right? Can we do that? Well, yes, we can. I'm not going to bore you with all of the gory arithmetic and moving things around. I just want to show you what we would do. We would simply take this equation and isolate t, solve it for time. So you would get time is equal to, what do you have? Final velocity minus initial velocity divided by a. You'd have this. And in this equation, wherever you saw a t, you'd put this instead. You'd do a substitution. Not going to do all that math, but if you did that, what you would end up with is another valuable equation. And I'll give it to you right here. Check this out. There's an equation that relates final velocity squared to initial velocity squared plus 2 times acceleration times displacement. Put that guy in a box because that guy is also very valuable. What are we relating? We're relating final and initial and acceleration and displacement. So you look at these, what are they relating? And say, well, they're each relating sort of a different mix of these variables. Here we have those, and we take out displacement, but we get back a final velocity for this one, and we take out time and put back displacement, and we have this equation. Okay, so here's where we are. Here's a quick recap of what's going on, what you're faced with. If we are relating initial velocity, final velocity, acceleration, and time, there's an equation you want to use. It is this guy. Well, I guess I could put the VI in front. Sorry about that. It's that. Okay. Oh, by the way, if you subtract this from both sides, you have VF minus VI, and that means delta V, and then if you divided both sides by t, you'd have acceleration isolated by itself. So it's kind of like, well, this is almost like that, right? Okay, never mind that. Kind of the same thing. If you are relating your displacement and your acceleration and time and initial velocity, then the equation you would want to use is this guy. Okay. Now, if you instead are relating a different mix, the third mix of these four things, displacement, acceleration, initial, and final velocities, well, then you would use this equation. Final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. All right. 3 very important equations that are very useful when you're solving problems about accelerated motion. But there's a couple I want you to also remember that don't have acceleration in them. But when an object's moving, you obviously have this guy, an equation for average velocity. Well, here's a short way to find it. Change in position divided by time, or displacement divided by time, right? Very useful equation. And you also have another way of looking at the average velocity, and we've seen this already. The average of 2 numbers. And the 2 numbers are your final and your initial velocities. So, yeah, paper. Cool. So you add the 2 numbers together, divide by 2, you get your average, right? This is also occasionally a very useful equation. All right. So, getting into more mathematics, you want to be reviewing these, you want to be trying to read about them and understand where they come from, but mostly becoming comfortable with these is going to require practice with problem solving. You will use equations when you solve problems, and it grows comfortable for you. Trust me. It's not going to be that big a deal. If you look at it all at once, it might be overwhelming, but with the practice, you will become more familiar and more comfortable and more proficient at using them. Okay, that's enough for now. Thank you for watching. I'll catch you next time.